Hello Internet, and welcome to Super Simple Scala episode 5. Today we will be talking about functional specifications. So in this example of a functional specification, we have a laptop monitor, which we will be performing transformations on. Each laptop has a monitor with a rectangular display. Boom. D for display. And it is rectangular, so this must be the same for all rows. The display has a width and a height measured in pixels. So let's say this is a pixel. This is a pixel, and each of these are also pixels. A pixel contains a color, so our pixel has a color and a brightness, which is an int. So let's just put int. A display is resizable, so it has to be possible to make this thing bigger. When resizing up, the resulting display must be an integer multiple greater in size and width than the original array. So for example, 2.3 to 2.6 is acceptable. So for example, if we had something like this, we could go to like that. All we would do is each of these singles would become a double, like that. So 1 becomes 2 in the sort of vertical in the horizontal direction. When resizing down, the resulting display must divide evenly. So it should be possible to sort of undo this operation and go back to the original. For example, 4.6 to 2.6. In addition, it must be possible to change the color and brightness. So this can change. So these are, let's see, changing. But that doesn't necessarily mean they have to be mutable. Reading a pixel in the display with given XY coordinates should take roughly constant time. So constant time reads, that means we're probably going to use a Scala vector, which is kind of like a Java array list. So let's say we're going to use a vector. The monitor has a back buffer where writes are made. When the monitor is told to refresh, a new display is made by passing the back buffer into the old display. The back buffer must always have the same aspect ratio as the old display, but there must be a constant multiplier, so everything must fit evenly. Okay. And then don't worry about extra credit stuff. Let's implement this, starting from where there are the fewest dependencies. Okay, so obviously we're going to have color. Case class represents an immutable class or an algebraic data type. So these are our colors. Sealed equals restricted to same file for pattern matching. We don't need to worry about that too much right now. And case class, they come with something like a copy method, and they're usually immutable by default. And then we have our pixel, which is the color, say it defaults to black, and a brightness of type int. We can define types pixel grid, which is a sequence of pixels, pixel column, which is a sequence of pixels. Now normally when I see something like rectangular display, it's really tempting to make a data type called rectangular display and have it sort of maintain all the invariants and stuff. And I tried to do that. There's a library that provides what's called dependent types. It's called, let's see, there we go. It's called Shapeless. And they actually have a dependent type for like a, for sort of like, I don't know how to describe it, like a grid with fixed, like a rectangular grid kind of a dependent type. But the issue that I've had with that is sort of you can append a single element and that works fine. But trying to sort of append different grids together of different types and make them behave the right way kind of causes problems. Also, it really messes with the type inference system in my IDE. So I end up having to sort of specify these really, really long types. So for example, this is a list of things that have a size, rectangular size, where the size of the rectangle on one dimension is equal to 3. Here, so dependent types encode information about data. So for example, in this dependent type here, shapeless.nat3 example, shapeless.nat3 in signature means that the width equals 3. So we've created a type for a rectangular whose width is 3, and this is compile checked when it's built. If you try to build something that has a width of 4 and you give it this type, it won't type check, it won't compile. Disadvantage of dependent types is that if you look here, you've got types for the different widths, but they only go up to what, 22. Obviously, you can't create an infinite number of types. I mean, you can't create an infinite number of concrete types. You can create, a type constructor that generates types and pass different types into it, but, someone has to define, type 0, type 1, type 2, type 3 for all the different rectangles. So, it provides a limitation on width, 0 to 22 or something like that. Also, you have this big type signature. Type inference has trouble. Scala wasn't really designed for dependent typing. That's more of like a, there are other programming languages that are designed for that, mostly for research, but yeah. So we could have done it this way, but that causes issues. So I ended up doing design by contract. Design by contract basically means that instead of enforcing these things at compile time using dependent types, you would enforce them at runtime using things like assertions or requirements. So for example, if you look at the display type, monitor display type, we have sort of this requirement. This width is less than that width. We have like requirements. We have something called verify rectangular, to verify that a grid is rectangular, and it throws some sort of an error if it isn't. This is a huge pain because you actually have to iterate through, you have to go through all the grids and make sure they're all the same length to verify rectangularness. Also, some built-in operations like appending together two rectangular grids don't really I guess come default. So for example, by default if you create if you create like a val t equals vector of int, there's nothing forcing, you've got, vectors of vectors, but there's nothing forcing these vectors to be of the same size, and you don't have a built-in operation to kind of take one vector of vectors and another vector of vectors and append them like this or append them like that. You have to manually go through the rows, and it's very cumbersome. But basically, the way that I would implement this resizing operation is I would define a function called grid transform, which extends function 1. I don't think you actually have to specify the out height and out width, the height or whatever is going out of it. But what you should specify is the height and width of whatever is coming in, just so that you can check to see that everything is the right height and width. So, and what this does is it will take in a grid of pixels, where a grid of pixels is a type that is a sequence of pixels, and it puts out a grid of pixels. And so what you want to do is, if you look at this drawing, you want to be able to say, here's the monitor, take this grid of pixels and map it to another grid of pixels. Then take this grid of pixels, map it to another grid of pixels, append these two grids of pixels together, like that, into your result. And then when you run out of grids of pixels, you are done. So we have one thing that checks to make sure that verifies whatever is going in is rectangular, because if it's not rectangular, you can't attach together. So you do in hook to verify that whatever is going in is rectangular. You do an out hook to verify that whatever is going out is rectangular. In retrospect, I should really define a class called rectangular grid that does all of this stuff, but that's something that really belongs. I believe that there are certain things that fit better into library code. For example, like data structures, and there are certain things that oftentimes fit better into like user code of whatever it is they're trying to do. And something like a 2D grid is something that just makes more sense to sort of have implemented in a library. But yeah, you can think of So then you verify that it's rectangular. You do this make grid function, which will be overrided. It's the only thing that's not final. And then you do this out hook function that verifies that whatever is coming out is rectangular. So we have this grid transform function. And what we do is we do a resize operation. We give the display. So the display has a screen of pixel grids. And we give this display a transformation of type grid transform, and we verify that everything is correct, and we have some hideous, terrible code that does this process of sort of going through every subgrid and applying the transformation and then concatenating together all the subgrids. Don't worry too much about this terrible code. But you do this terrible code, and at the very end, you slice it, you dice it, and at the very end, you appended things together vertically, you appended things together, so you appended horizontally, and then you append vertically, and then you end up with your final 2D data container of pixels, and then you wrap that in display, and then that's sort of what you get. The point of all this is this notion of HOF, higher order function. So a higher order function, HOF, It's like a function that takes in another function, sort of like map, reduce, filter. You'll see these a lot on your data structures. They save a lot of boilerplate. But basically what we've done here with grid transform is we've actually defined a higher order transformation, grid transform, which is actually a class that you can override. But basically this higher order function, you pass it in and the display feeds it some grids and it does transformations on these, and then the display, applies this function to the data, and then it concatenates the data together, and you have a new 2D grid of for the laptop rectangular display, right? So you have a rectangular display, you have a grid transform. So you have a rectangular display. You have a rectangular display and you have a grid transform, and you apply the grid transform on the rectangular display, and you do it repeatedly for multiple pieces of the display, and you get new pieces of display, and then you put those pieces together, and then you have a whole new display. What's nice about this? Well, it's a very, 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 very flexible way of doing it, and it also avoids mutable states, so you can parallelize things easier. So let's say, for example, that we were using our higher order function to do something. Sorry. There. No. There. Okay. Don't worry too much about this. There's actually some weird stuff that has to be dealt with, but let's say that you create a new monitor display, which is a 2x4 vector of pixels. You define a transformation. The transformation can take in whatever size you want. It can take in 1, 2, or it can take in 2, 4. If it takes in 2, 4, it'll just eat the entire display. It'll just eat the entire display. It'll put out a new display. If you take in 1, 2, it'll break the display into pieces of size 1, 2, and it'll apply the transformations to each of those pieces and then put those pieces together to make a new display. And we override the function makeGrid. We define a new vector. Let's say that whatever comes out, let's say it's like 2, 4, I don't know. So if you take in 1, 2 and you put out 2, 4, every little piece will be, if you look at the little pieces, every piece of size 1, 2 will produce a piece of size 2, 4. So you'll end up with taking these pieces and doubling each piece and then putting the pieces together, so you'll end up with a display that's twice as big. And while you're doing that, you can also set the brightness or the color of the sub-pieces. So for example, if you wanted to make it so that the entire thing has a brightness of 2, you would just say that the brightness is 2 for each of the sub-displays, and when it gets put together, you have a whole display of size 2. So you can customize color. When you do the mapping to make a new grid, you can customize the brightness. You can customize the color. So you can say whatever, color.red, comma, monitor.color.red. You can customize the brightness, you can customize the color, and you can customize the size. So you can say, do I want the size to double? Do I want the size to stay the same? And you can also kind of say for every 2 by 2, I want them to switch with the one next to them. So it's very customizable. You avoid mutable state, and you basically have one display. You map it to a new display, then you map that to a new display, and you can just sort of keep shifting by repeatedly calling makeGrid in the old grid and keep getting a new grid. And then you can call what is this, transform. So then you can call resize. You pass in the transform. So this resize higher order function. Why is it a higher order function? Well, resize takes in a function, applies the function to the data, and gives you a new data, right? And then once you have that data, you can do whatever, right? That's pretty cool. What's nice about it? Don't worry too much about the back buffer thing. Well, for example, what if you wanted to do this in parallel? So, for example, if you had 4 rows and every row had, a pixel, and you wanted every pixel, 1 pixel, to be turned into 2 pixels, well, you can parallelize the rows. So instead of having 1 thread that does all 4 rows, you can have 4 threads, right? You can do cool things with that. But yeah, I would call that, due to the the absence of mutables, well, due to the use of immutable data structures and immutable state, the presence of transformations on data where the transformations are applied in steps. Step 1 is map, step 2 is concatenate, step 3 is produce the new data structure. Because we have this sort of immutable assembly line of steps that takes old data and makes new data, we have a functional. One thing to keep in mind about functional specifications is that functional specification, it's almost like an assembly line. So for example, in this functional specification, step 1, make a rectangular display. Step 2, make a display mapper. Step 3, pass display mapper into higher order function to make a new display. And step 4, use new display. If you look at it, functional programming, oftentimes it's almost like an assembly line. You've got this data and you're applying transformations on the data. Object-oriented specifications, so OO specs, they're kind of like, message passing. Class 1 talks to class 2, class 2 talks to class 3, class 3 is actually, has a subtype, you talk to the subtype instead of the type. It's object-oriented is oftentimes you can think of it as like, this is talking to that, this is talking to that, this is talking to that, whereas functional programming, you kind of have sequential, map, 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 map kind of a thing. In addition, we also mentioned the difference between design by contract versus dependent types, where the dependent types can encode invariants in the type signature. So going back to our Shapeless example, extended header equals size type Shapeless natural number 3. So here we have a size type with a width of 3. If we wanted to append something to it and give it a width of 4, the type would change. If you wanted to append something that has a width of 4 to something with a width of 3, it wouldn't work because it wouldn't create a rectangle and the sizes won't match up. So with dependent types, things like sort of the width and the height of a rectangle are encoded into the type signature. If you try to make one of the rows longer than the other, it won't compile. Whereas if you're using design by contract, you would instead say something like in Java, if row 1 is longer than row 2, throw new, whatever exception, illegal operation or whatever. So with dependent types, we're enforcing these invariants at compile time, whereas with with design by contracts, we're enforcing these invariants at runtime. And I think that's enough material for the day. Thank you for watching.